So this is chapter 1 under vector notations and operations. So first, we will be discussing about, before we discuss about unit vector, let me define two terms. We have the first one, scalar, and the other one, a vector. So what is a vector and what is a scalar? So what's the difference between the two? A scalar quantity, this term, refers to a quantity whose value may be represented, it can be represented by a single real number, while a vector is a quantity that has that magnitude and also included the direction. So for scalar, this is just the magnitude, quantity with just magnitude, quantity with magnitude, only magnitude. While vectors, these are quantities that includes the magnitude and quantities with magnitude and also the direction of that magnitude and direction. So there's a direction. So example of this for the scalar, example for scalar quantity. The scalar for the mass, the quantity mass. So mass represents a number. This is just a number. It has no direction. So this is a scalar quantity. What is example for a vector? For a vector, we can consider the quantity force. The force is a vector quantity. Why? Because it's not only the magnitude of the force, but there's also direction for the force. So that's the difference between a scalar and a vector quantity. So here in vector analysis, we will be dealing more on vectors and also vector fields. So you need to know what are the examples of vectors and the notation that we will be using. When you see this will be our notation. So for a vector, so if we have we name that vector A. If you got a half arrow at the above of the letter, then this is a vector. This is a vector. While for a letter that has no arrow, then it's a scalar quantity. So this will be our notation. This will be the notation that we'll be using in EE126. And we will follow this one all through the course. And now, for the unit vector also, the notation that we will be using for the unit vector, if we have a vector r, if this is a vector r, and the unit vector a r, so or we can write this vector into different components. The magnitude, which is just the scalar part of that vector r, or sometimes we also put absolute value to tell that this is the magnitude of vector r, or we can also just write r, and it will be automatically this will be a scalar quantity. Now this is a vector, so we need to include the direction, and the direction will be in terms of the unit vector. We call this one the unit vector. It represents the direction of the vector, unit vector. So we'll be using letter A, small letter A. So this is specifically will be reserved for a unit vector. So there's a subscript here r. It means this is the unit vector in the direction of this vector r. But in general, it will be in different directions. It depends on the coordinate system that we will be using later on. And if you want to solve for the unit vector based from this formula, vector r, the unit vector, now the formula for the unit vector will be just the vector itself, r, you divide it with the magnitude r, the magnitude of that vector. So this will be the formula for the unit vector. For the most common coordinate system that they use the rectangular coordinate system. So in the rectangular coordinate system, or the Cartesian coordinate system, we have three different directions. We have x, y, and z. And we will discuss more about that later on in the later parts of chapter 1. So we can also, if we have another vector a here, we can represent this vector into its different components. If you are in rectangular coordinate system or Cartesian coordinate system, so the vector should contain the different components into the different directions. So for example, we have in the y direction or x direction, ax, this is the magnitude. In the x direction, ax. Then we have another component in the y direction, ay. Then another component at the z direction, az. So this is a common way of representing a vector in Cartesian coordinate or rectangular coordinate system. It has three different components. In the other coordinate system, this will also change. It depends on the type of coordinate system that you will be using. So if you want to solve for the magnitude of this whole vector, because if you look at, this is a rectangular system. So if you look at this vector, so if this is the z direction, this is the y direction, and we also have the x direction. So this will be the x direction here, and this will be the y direction. So a vector starts at the origin, a normal vector. We also have the other type of vectors, the displacement vector from one point to another point. And sometimes for the magnitude for the different components, sometimes we use just x, y, and z values instead of ax, ay, and az. It still means that it's the magnitude at x, the magnitude at y, and the magnitude at z. Because when we plot a point along the Cartesian coordinate system, it's in terms of the coordinate x, y, z. And that x, y, z, it means that's the distance between, or if it's x, it's the distance between the x-axis, the y-axis, and the z-axis. And that's actually the magnitude at each different directions. So here, if we have a this point here, and if we connect this one to the origin, this will be the vector. A vector from the origin. Let's say this is connected to the origin. So this can be a vector A or any vector. Then where is AX, where is AY, where is AZ? So if this point is plotted X, Y, and z with the coordinate x, y, and z. Then ax, ay, and az. Ax is somewhere here. Ax is here. This is ax in that direction. Remember, a unit vector is a vector. It's still a vector, but it has a magnitude of equal to 1. So this is the length here is 1. And also here, this is ay. And the one that goes upward, that will be az. So those are the unit vectors. Now, for the magnitude or the component of the vector A, we need to draw a rectangular because this is in rectangular coordinate system. So maybe this one. Then another line here. This point. So if this is the rectangular prism, so this is the vector. The vector is actually the diagonal of that rectangular prism. And if you want to solve for the magnitude represents the length of this diagonal. And if this is x, y, z, then this will be y, the distance from the x-axis. The distance from the y-axis is x, and this will be the distance to the z-axis will be z. Or in parallel with the z-axis, that will be z. So the length, width, and height of the box or the rectangular prism is x, y, and z. Or if this is a vector ax, ay, z, so this will be ay, this will be ax, and this will be az instead of x, y, and z. So if you want to solve for the magnitude of a, so we need to calculate the length of that diagonal here. So how do we calculate the diagonal of a box or a rectangular prism? So we just need to draw another line here. And by Pythagorean theorem, we can calculate this line. This is perpendicular to this side. This side is just x also. So that side will be equal to the square root of x squared plus y squared. Then this is also perpendicular with the az. So this is ax squared, ay squared. Also perpendicular with the az, and the hypotenuse side will be actually the magnitude of a, or simply a. So if we calculate a now, a will be just equal to the square root of this side, which is ax squared plus ay squared. Then you square that, then that's just ax squared plus ay squared. Then you still need, so this is just the adjacent part. For the opposite part here, the height of the triangle, it's just az, so plus az squared. So therefore, this will be the formula for the magnitude of any vector in a rectangular coordinate system. You just need to take the Squares, the sum of the square of the magnitude of the components, ax, ay, y, z. You square them, you add them, then you take the square root, and that will be the actual magnitude of that vector A. So this is the unit. This is the unit vector and our vector notation that we will be using in EE126.